not available with X-ray diffraction. Of course, the main part which is covering the non-destructive, and it is complementary to X-ray diffraction. We have to use together. And with this, I will be covering these two parts: structural magnetic properties of various metals using it on diffraction. So just a quick note on the data analysis, which is very much similar to your X-ray diffraction. Collect the diffraction pattern, reflect the atomic and magnetic models using modeling software like software, and to help the users to solve the magnetic periodically organize neutral schools and workshops every year to train research scholars and young facilities who know how to deal with the neutron data. This will do, one can go to this Neutron Scattering Society of India website and get information about where these schools are being held and will the government like is only one of like but and make use of the details. Now with this, I come to the magnetic part. So what happens? So here, neutron is a tiny magnet interacting with the atomic magnetic field within order 9.2 years. The magnetic potential, which gives you the magnetic cross section, which gives you the magnetic structure. By this expression here, you see length, and this is the actual coordinates of magnetic atoms, and this is the level. This magnetic scattering length, this interaction is being vector in nature. We'll see that the magnetic interaction vector, which depicts the angle between the scattering and the magnetic moment direction. Okay? With this, it turns out that neutron only see magnetic moments which is perpendicular to the scattering vector. Magnetic moment is in the direction of the any magnetic field. This gives direction to magnetic. But this is a finite factor for X-ray, as you already know. Learning from built-in neutron scattering is also very finite form factor because you can be nothing but some of the and that is now comparable because now they're getting only length of extra neutron, or extra. I see that there is a potential very high for it goes down very rapidly to 512. Still occur at no Q values only. So that one has to work. Please look at the typical diffraction patterns for ferro and ferromantic materials. So for ferromantic materials, you see that these are the nuclear bracketing. One is magnetic ordering, the extra signal, that you only get the enhancement of nuclear bracketing, no extra bracketing. Because ferromantic ordering. When you have a antiferromantic like this, and your university of your magnetic industry is derived from your chemical or nuclear industry. Yes, or antiferromantic ordering, then quickly you can identify what only the first indication that is drawn. So now this is the National Facility for Neutron Beam Research, which is situated at Dhurva Reactor, BRC. Dhurva Reactor from outside, Reactor Hall, and you might have seen this. Or you are welcome to Neutron reactants facility. This is well operational for I'm only going to show you the differential part. For we do PDC and for a single crystal diffraction. Here, I it is mainly used by university. This okay. In terms of sample alignment, I should cover this because we can measure diffraction data and it comes from temperature, our room temperature as well as low temperature, which we can put down to 1.3. higher five go up to then the degree, we can also apply 9 to 7 Tesla. But here one important thing is that the sample requirement is massive. So I can make 2 kilograms of sample is good enough. It will be a big process will be very similar to text. Need a large amount of sample, typically 1 second, that 2 to 5 grams of process to take order into the future. So with this, I now cover two examples of magnetic ordering in various materials. So first I see magnetic ordering in molecular magnets. Say iron hexavalent, uh, and iron other 3D metals. You get side with you can get different magnetic uh, the low density of the order of 1 centimeter cube, 1 gram centimeter cube, and they are also biocompatible. In fact, they are used to remove radioactive cesium from very inhaled instantly. Also, they have applications in battery and supercapacitors, iron storage, memory reactors. So here I show very simple example of this iron exercise item. That is constantly around 10.219 electron. Iron is going to very symmetric sides. Nitrogen, carbon going to 24 sides, where only electron is variable. Here one thing is mentioned that it is able to distribute carbon and nitrogen back by the element. Right. So this but later on it is very much possible to distribute this element. Now when you look at the structure of this compound, yeah, ah, this is the structure. You see there is a linear change of iron, carbon, nitrogen, iron to carbon, nitrogen along the Q edges. And these two iron are residing in different oxide environment, carbon and nitrogen. But the size of this oxide is quite different. Different magnetic activities. They should here, so here the here distance is 1.8. This oxide is bigger, so this is the slide is stronger. So, but this very dramatically change the magnetic properties because this iron is plus so it is splitting between energy Dr. But you see that once the unpaired electron goes here, the pole one has choice. Here or both, splitting energy is getting unpairing or otherwise. Here happens that more than pairing energy. So both is yes, yes, you have only one unpaired electron here. Ah, but it is just opposite for this other octahedron, which is bigger in size. So here splitting energy is less than pairing energy. If you have all five unpaired going to all these like orbitals, and the net spin is 5 by 2. And this spin is reflected in neutron deflection pattern. These are the two patterns. This is our body. This is so this is aromatic state, nuclear phase, which is the slide phase. Here, this line is magnetic phase. You can see that there are only the tiny enhancement of some red peaks. So that is a typical CDC for aromatic ordering, and you can model it. And but it found out that the magnetic moments of iron 3 plus nitrogen oxide, the bigger one, so it is 4 micron, corresponding to S is equal to 3 by 2. The other movement at iron 2 it is having only 1 whole micron, close to half moment. So this is the magnetic structure at 1.5 Kelvin. Iron 1, iron 2, lined along the Q edge. This is power of electron scattering, which gives you the signs of magnetic moment as well as their relative alignment. Now I covered the second example, which is the magnetic alloy compound, which is DYSE5A. The three magnetic sublattices, one rare magnetic sublattice. And the crystal structure, so it's a tetragonal structure. A and D are equal. You see the on and X pattern plotted together. See that there are that which is information for actually neutron work on differences. So now we look at the structure. So dy is going to this highly symmetric way. This is 0 here. And it is going to two places, 8F and 8J, which is also shared by CCSU. So this is K direct, but this is only 25 kilograms. Now we look at the magnetic properties here. The magnetic ordering is around 255 kilograms maximum, and then it goes down and it becomes zero and becomes negative. You know, compensation, magnetic compensation is happening in this compound, and this compound is around 93 calories. This is dark by our group very much because this materials there's like there is no bulk nitration, but there is a finite chloride. So here I mentioned another technique to show the introduction, but this is neutron depolation. Basically, polarized neutrons are interacting with the domains of when there is a finite depolarization of the beam. Here, polarization is as if there is no magnetization, which is at the same which is also having a zero magnetization. So this, as I showed, we have studied a variety of materials like in molecular magnets and materials. Here, you can look at value also on this molecular magnets. So how to understand this? So we look at the like a function of temperature. So this is the temperature pattern. You see, like yeah, I'll cover that. See that there's only one three bragg peaks will be, and then intensity is increasing. No extra bragg peaks. The typical feature of Carroll 39. And when you model this, you see the magnetic moments of iron sublattices. This is B, and they are anti-parallel as you can see. With the AB plane is equal to iron sublattice moment. And here you plot the net moment. Here it is dominated by iron sublattice moments, but at the lower temperature it is dominated by the dy sublattice. But the compensation around 93 Kelvin. So this is very microscopic understanding of this. The nitration is for example, I found anti-nuclear ordering in YBC. This is a perovskite materials. You already know they are also having a G-type ordering for chromate drive. Sometimes it is for C-type depending upon the state of the gas. Now this is also whereas the YB like I had right? And we look at the this is again you see a compensation around 16.9 Kelvin. You look at the signatures and it is ordering here. And again, you don't depollution and there is a compensation of movements because of the two equally but you see that some peaks which are absent above PM, they appear here. So this is experimenting on where the domain slightly the analysis is the polarized point plotted here. Basically, then by B. Decide whether magnetization is positive or negative. Yeah. And then I go to another example just to show that when you can detect lithium, also use X-rays. You can see the cation, how nicely cation and I distribution is shown here. So cation has the two of that are side in this compound. It also shows a relation in the electrical properties. Because one end is ionic and one end is electronic. We have the also shown the phenomena which can be explained as I for the previous study. You do the temperature dependent electron diffraction study. You plot the magnetic moment, and in that moment, shows the composition. Now we can study the electrical properties using this cool plot. So from this you can get the electronic and ionic part. One is the RNS type of conductivity, but there is a change of flow. That means your electrical is changing at the magnetic ordinary temperature as well as the composition. Electric degrees of freedom. Using this information, we can change magnetic structural and electrical properties. And now I so this exchange is not or looked along the free direction. It is the exchange has uh, layers in the material, but we also show this exchange bias applying in this negative magnetization material. Where this one to one correspondence. When magnetization is positive, exchange bias is vice versa. It's also seen in this compound when this compound shows negative magnetization and positive exchange bias, otherwise it's negative. So there is a one to one on application. Also, we can have the of magnetization from negative to positive by simply applying the different material. Third one is that anti-collective effect also changes its time. So you can use it for anti-collective and heating equipment. It's also very much known here. So in summary, I saw that construction from all the scientific and technical challenges. Thank you very much for your kind attention. This is our group member. Thank you very much for your kind attention.
Yeah. Thank you, Dr. Amit. It's really very exciting talk. So this is open for question.
Name of the property and practical application. Only one question.
Yeah.
Neutron, as we are talking about neutron diffraction. Name of the property is only one question.
So we are not directly developing applications, but as I said, this negative matters phenomenon, this understanding is application. Because battery have zero bulk magnetization, but there is a finite duration. It can give you the strict polarized current, which is you can use for like ambient applications. Yeah.
Yes. Other things? Any other question? Yeah.
Yes.
Utilizing this neutron diffraction.
Yeah, that is possible, but so far it is difficult to realize in.
Well,
But it's possible.
one of the group has done this,
Yes.
so
Yeah.
here we can do that.
Yeah, we can. No problem.
Another question related
Yes.
to the ideas. For the 5 nanometer
Okay.
to nanometer.
Okay, nanometer. Then we have to go to reflectivity. Then we can reflectivity.
We have
And we also have a polarized beacon reflectivity.
Last question.
Yes.
X-ray machines the doctors use. So can we use neutrons also in some part of the application? Randomly this.
No, because
I have no
see, neutron,
I have no idea.
yeah, neutron interacts differently with compared to X-ray. So X-ray you cannot penetrate the high jet. So that's why you get the image. Neutron will mainly interact with low jet like protons, like hydrogen. It can I mean good. No, no, not for medical.
Yeah, one question is from my side.
Yes.
I think yeah. So yeah, what are the other elements?
I did not show because of the time, but like sodium battery, this kind of thing is going on. So like sodium battery is the one work going. You mean to say? No, I am just saying from utility point of view, battery materials like what sodium ion. But yeah, that can detect with X-ray also. No problem.
Oh, thank you, Amit. Yes. You have to do a small estimation of
Yeah, yeah. Come on. Photographer साहब, where is the photographer? अब आप ले लो। मैं खींच लेता हूँ। अरे कहाँ है? अजय यार, अजय। उधर से नीचे से ले लो। लोग इंतजार कर रहे हैं तुम्हारा। आते तो जाए।
next up is also by a renowned scientist. I think we don't need introduction. Does anybody don't know him? Okay, so he is a professor at IIT Delhi. So, Dr. Thakkar,
Thank you, Chairman, for very short as my request. I hope I will be minutes. With this, I will thank organizers for inviting me and this opportunity to talk to all of you and share some of our results we are doing in RG Delhi. Well, I'm really grateful to Mr. Malik for this opportunity. It is new to here, but it is my first and to campus of this. Today, what I am going to talk about is some of our results. We are trying to study understand magnetic properties of some of the and discuss few of them. And in fact, Amit made my life easy, and therefore I requested organizers. Why Amit? He they already said about magnetic. So I will be talking about this particular series. Uh, Uh, the basic material is okay. So you may say that this material has been in the market research for a long time. What we are going to study here, it is really convince you that what we are doing is very new and contributing significantly in this area. And we have some students at both sides. Uh, Mobile replaced with niobium. Then we have this function. Now, we are going very quickly to what is called double perovskite. We are trying to understand, as I said, different magnetic. In the end, I will try to summarize. Um, so this particular material is having ABA3 type perovskite structure. You can see a rhombohedrally distorted perovskite structure here. Well, center, the green one is, and then your cobalt is somewhere here, coordinated. There are very interesting properties of LSCO3. It is non-magnetic, insulating ground. But there are many interesting things. Cobalt in this particular system is class. I will show you more details. there was the transition temperature of around 90 Kelvin. Also, as I said, the ground can increase by changing temperature. You have to increase it to be higher than room temperature around 90. The very interesting from the magnetism point of view is that, as I said, it is non-magnetic. Normally, we don't say non-magnetic. We normally are interested in ferromagnetism. And if it is some material is non-magnetic or interferomagnetic, terms non-magnetic. But you can actually tune the magnetism very doping. So as I said, you can go through the element and then change is a non-magnetic to something interesting magnetism. I will show you. More interestingly, what we say here in the LSE, one as non-magnetic dimension, magnetic. So a bulb LSE as non-magnetic, you change just the dimension either by making nanoparticles, going into LSE, change to non-magnetic. Non-magnetic. Right? Very interesting in that sense. What I said, the cobalt or no, cobalt exists in class, but we are consumers, capitals, they will try to respect, but the very interesting thing is that in this particular material, electrons, maximum in 3D, electrons can be filled. There are 6 electrons. Now there is some empty space. Ball is also that side is empty. Depends on you. You decided to go and sit on back. They have decided to go and sit on us. Everything is tight. No freedom. You have to find space, or if there is no space, you have to then go out. Therefore, these 6 electrons first they decide to go and sit in the lowest levels. As so, as is what as is the lowest spin state in this configuration. This is the lowest. And this is what I said. S equal to 0, no magnetism, no spin, spin, no magnetism, and this is what is the grounds. But now, if you just give small amount of energy to that electron, or you try to distribute that electron may decide to go from here to here. And that changes actually everything. Right? That means that now, while there exist, more energy or disturb the system again, right? It will happen. One more electron may decide to go. And that means now you have two. That is what the low state and something in between is what is called intermediate. Very interesting. What is the word? But on some of the parameters, you can go from non-magnetic to magnetic. That too changes from 0 to 1 to 2. More interesting thing comes here. Right? Particles. Then, of course, we all know about the moons. And very interesting stuff is that the difference between these two is very small, around 1 microwatt. Small amount of some in other reference, of course, it is. And that comes in terms of temperature around 35 Kelvin. So there must be something happening at around 35 Kelvin where there will be a break of parameter, but and also something happening around 85 Kelvin. Then it was studied, reported in literature that okay, the exchange coupling, Jones coupling, that fixed extent, that's in high speed plate. The other way around, no. At the same time, these were the two things were the literature. Then people said, okay, here in the structure, the cobalt is surrounded by oxygen, where cobalt is easy states of having two states. There will be, of course, some discussion between these two. They will be hybridized. That situation is predicted that you may have the situation where yes. Then, of course, there are few more important things. It depends on splitting depends on the cobalt done. And it is also said that if you have this configuration, of course, this is a one magnetic, I said, this ferromagnetic type interaction exists. But if you have some high ferromagnetic, one more. Of course, we started with a simple LSU3, but then immediately we thought of change. Let's replace AVO3 so that B% B. Because B we are saying B type. And if you AVO3 like this A, this point then we can say, oh, this is now called as double perovskite. Now the B and B type, they are arranged in this space. They are perfectly ordered. This type of B, B type, B type, and so on. Call it double perovskite, right? That is the case, and even though you can write like this, but you may not be able to call this particular double perovskite. Now I want to key double perovskite, but I control the ordering. I said ordering is B prime, B prime, and so on. From here, then what we will have B prime, right? More complicated. Cannot be able to because of difference in the ionic radial heat of B and B prime, the critical parameter to control this ordering. And also the oxidation state of B and B prime also important. B can be, for example, in our case, cobalt, and can be niobium. But normally exists in C plus, niobium exists in Y plus. So there is a difference. That's control or how to define this ordering. Like order parameter defined where the and B and B prime, right? And S equal to 1 here means completely order. That means A for 6, B for 6, B for 6. S equal to 0 is completely disorder. Then you will have two cumulative reactions and then B prime or 6. And it was observed that if you have this difference in oxidation state greater than 2 per ordering, also if you have difference in ionic radius, B prime which is more than 0.2 ordering. Less than it is. Of course, then and you can see CO is B plus, so that means that delta V order difference of around zero point 0.2 in the radii. So this will actually then give many physical interesting physical properties. So let me see this slide where I was trying to convince that this series of the material can be actually go less than side gone from 0 to 1 and then to basically convert cobalt 3 plus is sample, cobalt 2 plus in one sample. But second cobalt plus now if I change cobalt 2 to 2 plus, delta V here, what would be delta V? Any student? I'm now trying to change cobalt 3 plus to 2 plus, that's what I did here. You can see in this case it is 3 plus, in this case it is 2 plus. So my delta V is, बच्चों जोर से बोलो, delta V is 3 now, right? Niobium is in 5 plus. I said, थोड़ा सा ध्यान दो इधर, नहीं तो फिर so cobalt I'm changing 3 plus to 2 plus. So that means I'm trying to go from disorder to ordered state, and that will give me a opportunity. Anyway, we gone from 3D to and relatively favorable that go in cobalt 3 plus will be mostly in this range. Cobalt 2 plus would be by 2. So we try to study this whole series, and we recently published these studies in these. So as I said, we started thinking that LSCO, Lithium domain, and we can more recently, by how the disorder, as I said, we are going from disorder to the ordered state, how they are correlated. And of course, we used Absorption spectroscopy to understand the electronic properties, and also at Amit's institute, we use proton diffraction to study different aspects. So I will not go into these details. Of course, the synthesis is done by solid state method. Only thing what I want to highlight is that we have to heat this material at very high temperature around 1. The first thing, of course, we don't have neutron like Amit, so we have to rely on X-ray diffraction, and that actually our job. So diffraction from sample to one sample, or mesh and with treatment, and with structure and smell, or having. Of course, how they size is changing, size, size and sizes are given here. We all know this. What we have observed here is that are in the diagonal phase. Madam, I have stopped talking. You can switch off your camera. Don't worry. Please focus here if you want to learn something. The first three samples are in tetragonal phase. The last three samples are in monoclinic phase. All good. It was expected. More interesting was that you can see here the highlighted version are done. Then you can see here carry one sample. Of course, there is little bit of abnormality here in the behavior. Appearance is actually the indication of enhancement of the state. And that is what is expected. As I said, we are going from delta V to sample. The Raman spectroscopy, of course, is a very interesting tool where you can see for zero sample boards which are actually interesting. Important. There is no temperature, but you Raman structure is actually Raman in it. Now more interesting. You can see here this is the magnetization or the magnetic susceptibility, whatever you call it, doesn't matter. We are interested in we are how room temperature close to 0 Kelvin. Okay, 1.8 or 2 Kelvin. What you see here again systematically all these samples slowly increasing, and at very low temperature you can see there is a bifurcation between these branches. Branches are one reduction, zero field pooled data, and this data the so there is a bifurcation, and the bifurcation temperature is around 50 Kelvin. Simple 2.4, where still bifurcation, the bifurcation temperature is actually going down from 50 to roughly. Further increasing the concentration, you can see here this is around 6. And then suddenly what we saw at concentration 0.6 sample, now you can see very different behavior. Ferromagnetic ordering. I'm sure you all know the magnetization versus temperature behavior or ferromagnetic behavior. No movement start to increase, then it's magnetic. Increase, then it should increase and then go down. That what we call here in this case real temperature. This temperature magnetic ordering. Movements will then align antiparallel to each other and the overall movement will go down. This is what you can see here in these three cases. Temperature, what is real temperature? 10 Kelvin, then it is. So, don't worry too much about this. They follow each other. That we oops, our chairman is very strict. So then I will skip few things. So here we actually think, so then this 1 by pi we have plotted inverse, right? How Curie voice law plot movement, what is called, right? Effective movement then will give you the idea about the spin state of mobile, and you can see here the movement. Black dots are the experimental data. You can see here this is the sample movement increasing and then slightly increasing. Consider as in the high spin state, but then the cobalt 3 plus in high spin state and intermediate spin state and low spin state. Considering all those combinations of the, the concentration compensated of cobalt 2 plus 3 plus, lines, the blue one, the red one, and the black one. Both are in high spin state, the behavior, but our experimental results, the blues are solid. That tells me that both not in high spin. Right? This can be a combination of high spin state, intermediate spin state, or high spin state, low spin state. Considering understand where there is a transition from state transition. The magnetization was achieved with what I said. We did the measurements at very low temperature, like 5 Kelvin, temperature is below the transition temperature, and then the 30 Kelvin, which is significantly above the transition. Uh, Another interesting aspect is here you can see the magnetization, but sample now and 1 and so on. And what is interesting here is bifurcation temperature here is roughly 15 Kelvin. I said before, lower temperature where the magnetic of each temperature is a signature of magnetically disordered glassy nature. The glassy nature is where the ferromagnetic ordering and antiferromagnetic ordering they are working with each other, and then there will be a kind of very interesting structure. Behavior was there for other things. To understand the glassy behavior, we have to then do this magnetic susceptibility measurements. Again, on this hand, this not the DC. And for these three samples, you see here these measurements are done at different frequencies, and the frequency transfer of this is that when you do these measurements at different frequencies, and this is what was observed in this sample. But then the other higher concentration sample, you can see here similar measurement, but the peak position, here I am sure you get convinced that the peak position is like shift. You can see here one significantly. Here you can see for this sample, no change. Second, that these the heat specific heat measurements. Let me see here about instant gas. Amit already discussed. Again, the accent wise, as Amit also said, that normal magnetization versus magnetic field measurements we do in the zero field pool. What we do, we put the sample in zero field at lowest possible temperature. And so let's say 5 Kelvin, and then we change the magnetic field and measure the magnetic. We actually cool the material in different tubes. That will actually the behavior. You and then did fitting and try to find out the magnetic ordering and whether there is a presence of magnetism in material. But then what you can see here is the loop actually has Amit beautifully showed you the sketch. Showed yeah, the sketch. Here, so you can see here between zero field pool and the 20 KOE field, one loop per and that you can then plot as a function of CM here is not the crystal cooling field. So when you change the cooling field, what it can focus on the action by parameter, and so if you increase just at very high field get, and we then of course did a lot of analysis and try to understand the parameters uh, on this. We skip we actually try to study the or when man stops me, I stop myself. Conclude to use experts one to study like this. Want to understand different competing magnetic orders, the ferromagnetism, glassy behavior, and then of course towards the end, and we are now trying to study same series of one thing out of these six, utilizing one would like to thank my friend all work post were done in KIT and I don't know I have not shown you here, but we actually used X-ray at Indus where we different properties, local structure, funding agency, quoted our work.
Yeah, thanks for wonderful talk. Talk is open.
You are expert. I'm afraid of having.
I wanted to ask from there that conductivity. There is a huge change in resistivity and the DC.
No, it is not TC. No, no, no. We have not reached actually there. You can see I wanted to show, but I'm afraid of our.
So on me. Games on me.
382, 200 Kelvin or so. But below means
high resistivity we could not measure with the system. That's one sample is highly insulating and we could not even make uh, so, yeah, in resistivity, I don't think so. All these are normal resistivity. So, of course, yes. But so cobalt 2, so what we are doing here, basically going from here, this is cobalt 3 plus, and this is cobalt 2 plus. This is more insulating because it is in high space rate. Then, of course, by doing this standard model analysis, an energy and the density. Any student? I don't have chocolate, otherwise I have given them.
Sir, I want to ask you, suppose we have a system in which we got mixed oxidation state. So can we call such systems as double perovskite structures?
See, double crossment, I said ordering is important, not the oxidation state. Oxidation state will favor
Yes.
to have ordering. But in the end, the parameter to call it double perovskite or single perovskite is the ordering. But in one sense, no. So 2 plus 3 plus 3 plus 4 plus. You can do anything with the double perovskite. If oxidation is right greater than 2, then it will favor the ordering. Ordering.
Ordering, you're telling that delta V should be greater than 2.
That's what I said.
So how can we find this, like telling any material as a paramagnetic terms of oxidation state only? How can we find it?
वही तो बोला इतने देर तक मैंने आधा घंटा क्या बोला. So you just do magnetization measurement, magnetization versus magnetic field, right? So we know Curie temperature, right?
Yes.
Above Curie temperature, it is in paramagnetic. There will be no movement, no magnetization. All movements, even if there is a electron, all are randomly oriented. So magnetization would be zero. Then when it comes to the Curie temperature, the magnetization suddenly start aligning in the direction of magnetic field. Movement will start almost sharply. There is a and then below that temperature, then it will be like more or less constant. This is the situation for a pure paramagnetic transition.
Sir, one more question.
Neutron diffraction, of course, but we are not that privileged to have neutron diffraction.
I just looking at the XRD data, like, is it possible to
I think we can do it. I have stopped before time.
question, like, by just looking at the XRD data, structures, and of the same material, some papers have reported double perovskites also. So we have data of XRD data of cubic structures and some double perovskite structures. The XRD data looks similar. So how can we see that double perovskite unities of
Very interesting. So I showed you, like for the zero sample, one sample, there are few ordered, few reflections appear in the X-ray diffraction. Okay, so those if those ordered peaks are there, you can call it double perovskite. It's anyway very and if those ordered reflections are not there, then it is a single perovskite. Calling a double perovskite, we have to be very careful. Then not only from X-ray diffraction, then you have to also like I showed one spectroscopy. Where for Q normally is Raman active, Raman imaging. So you will not see anything, any Raman mode. But for double cross type, ordered phase, you see sharp Raman modes. That's what I showed you, a systematic variation in the Raman mode intensity. When we go almost disorder, I cannot say double cross type. Okay, this is like a single cross. Then going to products, Raman mix around very. Then of course it should be consistent. So, Raman and Samadhi.
So very interesting.
Yeah, and you can ask more. Of course, don't spare him. You can ask more after.
Really? So,
Yeah.
The same question, sir. Using that you have said Yusuf sir have data and
no, my data I have interpreted, not used.
no.
I have used his facilities. XRD से नहीं कर सकते।
XRD है न्यूट्रॉन से
न्यूट्रॉन से तो सर ने मेरे से ज्यादा सर हाँ रिट्वीट से करना पड़ेगा
रिट्वीट दोनों के लिए है ना
न्यूट्रॉन डिफ्लेक्शन will tell you the magnetic structure it is ferromagnetic or of course it's only the nuclear part और मेरे से ज्यादा एक्सपर्ट अभी सर आने वाले हैं
What question later? Give time. Small token of appreciation from the organizer. Sir Rajendra Singh Data. Let's move to the next talk. And next talk is by Professor Vivek Kumar Malik. And he is also professor of IIT Roorkee. And more than this, he is my senior. More than enough. Yeah. Thank you. So, his title of his talk is Magnetism in Complex Oxide System.
So first, I would like to thank organizers for inviting me to this nice conference, and as well thanks to the chair for introducing me in a very nice way. I'm going to speak about magnetism in complex oxide systems, and these complex oxide systems are basically, I mean, one of we used to call them as like a strong correlated system. Point word. The new properties in the system, for example, conductivity or insulated metal condition, or even say colossal magnetic resistance. So as a result, these materials could have a potential applications for um, devices. So one of the example is, or classical example, is manganese. So in these materials, manganese as a function of the doping, iron, the function of doping and the temperature, we see a phase diagram where we observe different types of electronic and magnetic. For example, the optimal doping around low open. Magnetic insulating fields. If we apply it to field, um, What I'm going to speak today, or I'm going to discuss, is a material something called orthoferrite. So these systems, where again R is the trivalent rare earth ion, instead of manganese with the iron. The few they are, so, but this is a thing. Here we do not see any low low temperature. This magnetic spectrum, we see the in the magnetic neutral diffraction, and that's how we can analyze. So, different ferrite, this so ferrite see the most like switching, negative magnetization, as well as the magnetic compensation. So as a result of that, the air movement as well as the iron movement, so as a result of the competition between the two, see the magnetic switching, magnetic compensation, as well as the negative magnetization. So these materials found on the I have dynamics is of second, which is the ferromagnetic materials. So this uh, near the room temperature also. So these materials can be utilized in magnetic devices and get a so I'll take one example, neodymium iron oxide. Below the just below the high temperature. So and a particular type of take like 1 unit cell 4 3s4 and define them the four spins. So S1 and S3 they are aligned aligned in different directions. So as a result, the interaction in this system spin component that axis. So this axis to the electromagnetic component along the C axis. That's why we see if I field along the MZ direction in a single crystal, the finite moment in this system. So one if we lower down to the temperature, something like below two temperatures, they keep their order built in this PC thing. So and their weak magnetic component also starts to rotate, and at low temperature, like low this weak magnetic component axis and antiferromagnetically aligned moment aligned along the C axis. We see in the magnetization result, we see that along so the lower temperature there is a C type that movement. This is the difference here is that this shows an abrupt magnetic bottom line aligned along the And from the extension movement, there is a anti-ferromagnetic movement along the Z. So still the near temperature is very high. Gamma 4 kind of a magnetic there is an condition below which this weak ferromagnetic thing, uh, and there is a canting, but exists in such a way that there is no weak ferromagnetic any excess. So then ordering and ordering things are aligned magnetically along the wire. Apply a magnetic field along the C instead of having C direction. Actually, we also see a polarization also. Polarization along the C axis. And this another is which we have used is RPM in high temperature. This is uh, uh, one. This shows a gradual transition between. Similarly, this another class of the chromides, they also show similar kind of behavior. But the only in the 100 for most reorientation. For neodymium, Maureen, this is so what is the reason? There is 4F and 3D electrons because of the layer of 4F is an isotopic part of the exchange interaction which plays a role. So these iron moments are ordered in the high temperature phase. Lower down the due to the weak ferromagnetic movement of the iron movements, these rare earth movements also starts to kind of polarize. They start to polarize not but also have certain symmetry as from the section. There is an exchange the iron movements perpendicular to their alignment. So as soon as this we lower down the temperature, this rare earth movement starts to increase. The value, the magnitude of this rare earth movement starts to increase. As a result, the strain inflection is also increases. Due to that, this movement starts to. So the point is, what is the role of this movement and what is the role of this iron field? So both we have to substitute iron with manganese as rare earth. Means we will not discuss about the sublimum dysprosium iron oxide. Uh, Interesting. I mean, I would like to come back to the question the student asked. People if uh, uh, that I mean, example, this gadolinium, just know this could be double perovskite manganese. Alternative way, this could this could fall as the double perovskite. There is a large value of iron and manganese because X-rays are scattered primarily by the electrons around the this, uh, um, this let's say for iron movement, iron or manganese. So form factor of the X-ray form factor of iron and manganese are quite similar. This particular material, for example, we will not be able to identify using X-rays. One thing you use their potency. This ordinary takes in the entirety and can observe. But abilities are quite similar. In this case, neutron scattering can happen. This is the neutron scattering depends on the z value of the atoms. Yeah, neighboring different different case we can identify whether there is a double Pascal node, irrespective of the magnetic ordering of that protein. Similarly, here also, we see this pattern of time. This, it's like these are the four samples. That, phase analysis, whether it's a single phase or not. And then since we did the neutron diffraction measurement, this is the structural data. I'll discuss about the magnetic data, but this is um, uh, like and the latest constant. Uh, so this is the typical, our first thing is that, okay, let's do the magnetization measurement and we see that at not seeing much change in the magnetization data. I mean, using this, we cannot conclude what is the structure with this. What this is not possible. Say, yes, some transition. And from the MS loops also, we see that magnetic, which should not be because this is a I mean, antiferromagnetic with a ferromagnetic component. That's how as still more or less the same. Using this data, I cannot conclude much, at least about the magnetic system. Whether was it who that to the magnetic have already introduced from the so neutron diffraction and using the neutron diffraction iron as well as the so for example, even at the room temperature, magnetic fields, but I mean, what we found, and then at very low temperature, we also start to see new peaks, which basically emerge because of the annual total. What we found that at the high temperature, the is runoff bits gamma 4 and gamma 2. This those the structure. So from the intensity profile, see if it would have been equal, if intensity of one peak, another peak, because it is like one of one third, and then we say this is like gamma 4 without doing the analysis, and we then around like 70 um, so so in the layer ordering, the structure of this iron movement should be having the symmetry of gamma 1, but we could not. Uh, then I'll quickly show, before summarizing both the levels, we around 400 stability near to the Nile temperature. We also observed the critical where we can change this from negative to positive and low temperature. At low temperature, of course, we using the again we get the neutron effect measurement. Since our low temperature case is kind of there is no and kind of an it changes abruptly from one structure to the other. In this case, earlier case, some of the orientation and considered complete reorientation. And then observe the gamma both by have this multiple kind of and yeah. So with also, I mean, operators from IIT Roorkee side, these are the two. Gitanji and Sarita, these are the two. Did some the calculations and PLC and
Yeah, thank you, Professor Malik. It's excellent talk. Insightful. Thank you. And now talk is open for question. Yeah, any question? And okay, so one question from my side. I want to ask him, but I will ask you. So there, if this is ordering, then there must be a lattice mismatch.
uh,
Go mismatch of whatever you have ions.
okay, there are two things. Is the one thing with huh?
Yeah, what we call B to B dash ordering.
This cationic ordering.
Cationic ordering.
Yeah, I mean, there of course would be lattice mismatch in a way that there would be one type of lattice is different. Okay, this that would have some kind of an uh, lattice mismatch comes when we talk about the thin film and like that because you have substrate well defined. In this case, whatever the lattice parameters would be, it's another type of sometimes you may find this
mismatch in the strain, what we are talking about mostly in thin film.
Thin films where lattice mismatch is usually large and then
Yeah,
bulk material. Yes.
And we are placing it in simply in between electromagnets, and we apply magnetic field in both. In first case, parallel direction. In another case, perpendicular direction. Is there any possibility of spin orientation there?
Good question. In case of usually for the powder samples, the orientation is random. But I mean, for the single crystals, of course, the crystallographic direction, parallel and perpendicular directions would have a certain meaning. But in this case, because it's random, powder is randomly oriented. But usually they are known actually in the case. When you prepare, it's president the form of palatal sound. When you do it, there could be certain grains which are against it. So if you look at, so that's why in certain sometimes in certain cases in the powders, although they should give a completely random nature, but in some cases some directions direct. But of course with the powder samples it's not easy to identify which graphic directions they are. In this case, usually we see the signature. That's what I said. Much from the magnetization data that you put in the magnet and then you measure the magnetization. More case of crystals of things, of course, can identify the crystallographic direction and then from here direction and the
okay. If no question, then thanks to speaker. So it's a tea break now. We will assemble after 10 minutes. 10 minutes में time मिलेगा? हाँ, बोला ही उन्होंने। वो उनका उनका correct हो गया ना। ये ना इतना दिनों तो घर में चीजें आप नहीं रख रहे। ये पता है कि पुराना है। फिटनेस पर देखें।
क्या लगा कैमरा होने क्या होने
Yugandhar. Yeah, please. Uh, Maybe due to some safety issue of women empowerment. Okay, we have to take a talk before you. Yeah, because it's our responsibility that a woman can reach safely at home.
My voice audible?
Yeah, audible. So, Silpa, without wasting time, so I welcome you all back to the technical session too, and we have a one oral talk, oral presentation by Silpa Rana. She's from DPU. Silpa, over to you.
Huh?
You have 10 minutes only. Okay.
So, good afternoon, everyone. Myself, Shilpa, and I am working under the supervision of Dr. Bharti Singh, which has already delivered her talk in the morning. And my topic of today's presentation is the PVDF boron nitrogen code of RDO electrical nanofiber based flexible tricoelectric nanofiber for the wastewater management. Every man has presentation. These are the outlines of my presentation, and with first I will briefly introduce about the major problem that we are facing today is the increasing energy demand and what are the possible ways through which we can overcome this problem. The experimental section we will be mainly emphasize on the materials and the fabrication technology that we are using for fabricating the triboelectric therapy, followed by the results in the potential application of the nano. So as we all know that energy demand, most of the energy demands are driven by the growth and urbanization. You know, these energy demands are fulfilled by our fossil fuels and other non-renewable sources of energy. They have the disadvantage of night and environmental costly. One of the possible ways to overcome these problems is to harvest the energy from our living environment. There are several types of energy present in our surroundings, such as sunlight, temperature, which is the advantage of this presentation. The focus of my presentation will be on the harvesting the mechanical energy. To harvest these different types of energy harvesters has been designed such as photovoltaic device, thermoelectric devices. But for mechanical energy harvesting, we are having the piezoelectric and triboelectric nanogenerator. But I will be mainly focusing on the triboelectric nanogenerator. Triboelectric nanogenerator works on the principle of the contact electrification and electrostatic induction. One of the needs that we require for the triboelectric nanogenerator is that we must have two materials. So we have wide range of material choice. Like that, and we need materials to help. In this process, when come into the contact region with other, a transfer of charges takes place. By adhering the electrode on the both the materials, we can collect the charges and can be used to drive our electrode. So these are the different modes that Nine has already discussed about. These are the possible modes which we can fabricate. So mainly we are working on the solid triangle. The assembly that
the solid or liquid assemblies also, solid and other assemblies for fabricating the triboelectric. So this is the triboelectric series of the materials. So for fabricating our device, triboelectric, we have said that we need to choose the two different materials to make electronic. So based on these, because of the fluorine containing elements, can be further confirmed by the KVFM measurements, and for the positive material we have chosen the nylon. So why PVDF? I think that I will need to skip because of the less. So there are different ways through which we can enhance the performance of the triboelectric nano generator. So one of the easiest way that I'm offering is the application of the nanofibers through the electrospinning technique. And another approach that I have used in our work is the addition of the 2D nano to the output performance of the nano generator. So these are the XRD measurements. So I have bought boron nitrogen code of the archive to enhance the beta phase content. Beta phase content is the electroactive phase of our polymer. So higher the electroactive phase, the more performance will. So to calculate the beta phase of the content of the we can see that the doping the content is from 75%. In the dope, 1.58 percentage of the boron nitrogen code of the RGO. And these results are in consistency with the increase in the content of the boron doping. The electric constant materials. These are the surface formulas. Low weight is formed in the synthesis process. For for the triboelectric nanogenerator, the surface potential is the one of the measured that defines the output performance of our nanogenerator. So to calculate the surface potential of our materials, we have done the KPI measurement. Again, the potential difference between the two materials, the more charges it can generate. So we can see that for the PVDF minus 0.98, can be used as a negative triboelectric material for fabricating the and the nylon has a tech potential, surface potential value. See that when we are doping the colors in the favorite matrix, the value of surface potential increases to the further minus full visibility possess negative polarity and shifting this surface further into the negative range. So to analyze the performance of our nano generator, we have our nano generator with the help of electrodynamic shakers. The output performance in terms of the open circuit voltage and the short circuit current measurements have been calculated using the oscilloscope and the electrometer. The content of the value of the voltage and current, maximum voltage of 242 volt and current of 4 microamps obtained corresponding to the 1.58 percentage of whether the effect of force and frequency has been also analyzed to check the performance of the nano generator, where increasing the force on the nano generator, here the contact force is contact area. Later, similar results have been obtained for the frequency variation. In addition to this, for further to verify our results, we have chosen different materials also. So we have chosen the one material for material, and we are changing the second triboelectric material to keep the same. They're saying no, like two materials should have the different energy. So it can be observed from these results the nylon when we couple the period film nylon and the load matching studies have been calculated because for the practical application we must have the matching load resistance to this output performance of the nylon generator by varying load resistance. But it's also important show the negligible in the finally, to demonstrate the potential application of our nano generator, we use the power generated by the nano generator to drive the thermometer, micrometer, and electrical box. So we remove the batteries inserted in this, connected our nano generator. The corresponding circuit is also the power. So we can say the nano generator is because the output generated by our nano generator is to drive our devices, we need our this performance to be converted into the DC. So this is the sound what it shows. So that don't need to add the battery there. So self-powered device for your nano generator. Mainly, the potential application of our nano generator is used in the for wastewater purification system. The earlier lectures we have studied the photocatalysis and other techniques for purification of dye. So here the power generated by nano generator is used to generate the dye. Also, the local techniques because it's so current, and we use these results for degradation of dye. So we to reduce its time, we have also used our materials boron nitrogen 4 dose as an electrode as well, which takes a smaller time our nano generator the for driving corresponding for my children.
Can you show me the image of nano generator?
Nano generators, actually, it's the process is like this. There is a thermoelectric generator. So red one is our nylon film, and the blue one is our PVDF film. The yellow one is where the aluminium electrode. You can do it by using technique, or you can simply just yeah. Product is not yet in the market because the current produced by this nano generator is still low. Is still low. It can be further improved when because there is an electromagnetic generator. Current value is what it is really high. So we are hybridizing the triboelectric nano generator with the can boost it. It's the triboelectric.
So product are already in the market. Companies are selling. It's not like that. You are doing the mechanism still. Okay. Okay, thanks. यार फोटो लेगा इसके कविता ले ले आ जाओ जल्दी आओ जल्दी
मैडम इधर मैडम इधर थैंक यू
next talk is invited talk and let me prepare myself. Talk is by Dr. Yagwendra Pitla. He is MSc from Karthik University in 2004 and obtained MPhil from University of Nepal in 2006 and 2013. He worked as a postdoctoral fellow at National Hong Kong University, Taiwan, and Indian Institute of Science, IC Bangalore from 2017. He joined Central University of Rajasthan as assistant professor in 2009. In Central University of Rajasthan, his research focus on nanoscale magnetism synthesis and characterization of complex oxide and different fragment phase transfer critical phenomena, electrical electronics, and so on. So, title of his book is Unveiling the Magnetic Nature of LASRCOV. It's over to you.
For we thank the organizers for giving the opportunity to present our work. We are mostly talking about human rights. And before I start my presentation, let me thank Dr. Nancy, who's part of work which I'm going to has analyzed some part of the data here and other collaborators also. What I'll do is I'll briefly summation of the talk is about kind of quantites and especially focus on the nature of magnetic order, right? And try to discuss some resolve the constraints and the of magnetic order. Doing so, I'll just try to elaborate on this transition. Finally, I'll try to make few concluding remarks. And before the beginning, anyway, I'll just yes, Dr. Amit and Dr. Archana, who has already extensively this study does context by and large most importantly, multiple yes, uh, has been close to model system tell for this is LA.5 SR.5 from here is having actually magnetic condition. And they have around here, and this system is particularly important from oxygen liquidity point of view. Changing the relative concentration of the solution by just waiting for solution, you are able to. So this I'll try to skip because the perovskite units structural cell has been discussed by the VFS, so I not dwell much into this. Most important point which I so is about this is like depending on the relative strengths of the crystal coming from the hydrogen, how that compares with the carrying energy. Whether these states are yes, or whether they are in those things. So, the that corresponds to
of the order of which double exchange by the intervening oxygen between the heterovalent whereas the homovalent bond ion responsible for the okay, now before I just go to this particular aspect, since I'm interested in the nature of order disorder transition, by word order and disorder transition, just going to that this system I'm interested in look at what is the nature of ferromagnetic to ferromagnetic phase transition, especially this nature of the interactions, whether there is any interactions, underlying interactions, video. When you the outcome of is that point field, this is a point field system. And systematically, though by variant, what is the effect of that? We will also try to see. Before I go further, I'm just trying to say that I'm interested in this particular phenomena. This is technically the study of the phase transition across the point, and this is generally quite in terms of experiments, which give me idea about which university sort of this position belongs to. Before I go further, I'll just try to let a high temperature paramagnetic phase. Paramagnetic phase, not in this direction. So just what happens is one kind of picture, secondary phase starts changing, and as I keep on changing the what is it, the parameter or slow temperature, what will happen is secondary phase fix the expectation ultimately times of will be the second. This is one kind of phase. So this is the nucleation based phase. On the other hand, you have another type of phase transition, which is I haven't initially started with this, but it goes into another kind of phase, and I keep doing this this kind of phase transition is like you have this kind of, very what to say a very complicated picture where you have a combination of these two phases. This must be referred to as electronic phase separation. Like you have the transition with the order magnetic order disordered phase transition. Those two happening. That kind of situation you have a transition like this, you have combination. And finally, you have something called hybrid kind of transition, which is very, very complicated to study from the chemical. That we just try to have a system like this. One of the background transition you keep constant. The background phase to try to keep constant, and only the since I said that I'm mostly interested in the very smaller disorder, they are modified in terms of various exponents. And all these systems which show this order disorder continuous fixed transition are supposed to follow civil power law. This law are supposed to be followed only at this, only in the asymptotic critical region, that is this. If you see there should be some corrections to this power law, and this line critical export they are related to it by this. Today I'll be mostly talking about bulk magnetization data and data to make it what's important. And now here I'm just trying to show you the theoretical expectations for various systems. So here D represents the space dimensionality and N represents the order parameter dimensionality or the spin dimensionality of the system. One, it's one dimensional system. Whenever I say N but one is in system, I can do this. If I say that I have D equal to P, N equal to P, into the system Heisenberg curve. Okay. And this three-dimensional Heisenberg curve and it shows similar to color transition is equal to gamma 1.386 coming from. And you also have long range so-called mean field kind of exponents, which is where typically the fluctuations of your order parameter are not important. So now what the main idea is to look at the phase transitions and then try to look at only such kind of phase transition. So here, before I try to go further, why we have taken up this topic, that I just try to show you this electrical system itself, various reports on this system in terms of the exponents, and you see that reports, what are presented here, they show exponents like uh, uh, the Heisenberg, the Heisenberg radiation. There, like, so there is one more particular situation where there is very much ambiguity, because whenever you talk about critical phenomena across a phase transition, the system is supposed to be governed by a typical universality class. You see, critical experiment belonging to one universality class below 20 and with this, but in this analysis, in this religious values, this kind of issue, but we just wanted to this 8.5 and S0.5, and we will just look at what is being reported about it. So we have seen that there are also these kind of picture like this. There is a school of thought that is divided between people Mr. Heisenberg yes, and some yes. We just wanted to see what is the issue with this. Fundamentally, issue in terms of data analysis or data collection that we wanted to see. This is the people say just systematically try to put vanadium. Sees that when you put vanadium, system becomes more complicated. This concentration of 45.5, plus this is one complication, and more in above, you also have the complication that. So, in addition to this complication, when you are trying to put vanadium, you are going to put plus ion. Technically, your system is going to be a ferromagnetic in terms of the magnetic because exists. Just trying to look at science what's the nature of this sort of condition. And but we just try to prepare this sample, the solid state method, and but externally measurement in the system. Practice the robot induction. This and just to show that we have the robot head structure is intact. We try to see what is the values of vanadium. Vanadium in technically from XPS, what we are trying to conclude is that is coming in the system of vanadium. What is cobalt concentration is increasing at the but this is the kind of conclusion we are just trying to get. Yes. Radiation measurements in the zero field mode and field mode, and we see the reflected magnetic reverse. And we are seeing that this magnetic reversibility is also strongly affected when this vanadium substitution takes. And from here, we are just trying to look at the transition way in which manipulation falls as a function of pressure is still sharp. We are trying to say that the order disorder transition is. vanadium in future. And on the other hand, we just try to look at the magnetic hysteresis loop, and from there we just try to calculate what happens to the hysteresis. And the important point with vanadium is that the moment you try to bring vanadium, the TC of this particular compound systematically increases with vanadium. Unlike most of the substitutions which are done in the cobalt network, this is also something peculiar. So here we are just trying to say that the magnet is enhanced, the vanadium is more low. And this graph only I just trying to tell you that the system is having metallic kind of nature. Point which I'm just trying to say is that the magnetic order disorder transition is there in the ferromagnetic, there in the metallic background. Metal inspector transition kind of thing is like not metallic. So the macro resistance value is also not that. Volume, like you see that the parent compound is, but then your volume increases in and cobalt, cobalt, oxygen, cobalt, bond angle, sorry, bond, this theta increases, and then you also have the valence is also just to what is the formula in which what is substitute. We have proposed two values based on all the observations. Scenario where explains this data quite well. If I carry out the uh, susceptibility data is analyzed at the HM transition. Here, the intrinsic susceptibility is related to the measured susceptibility inverse, something like this. The measured inverse measured susceptibility inverse is filtration factor, and this called exponent. Then, as a function of temperature, I use the asymptotic temperature, which is basically zero. Exponent gamma is typically three-dimensional Heisenberg system. So remember that this particular point exists. We also know that this system has precious spin gas behavior. So I will try to skip because my focus is on the order and disorder. Here only this only we need to keep it in mind that the gamma is three-dimensional one, which we got from AC system. Now the actual issue starts with the image isotopes, and this image isotopes are routinely done. They try to do the critical analysis. They don't try to modify the whether they just what you are supposed to minus schemes. One is the so modified electron, or I just minimize the analysis, which is this modified electron. Here we just try to take the values of gamma and beta to the minus zero, and which relation of beta and gamma gives parallel to each other. Kind of such kind of chaos in the past looks probable to speak. But this D and N represents various universities. That one is over. In field is most for this analysis. And now this thing you do is you this resistant method to try to get this will give you this continuous equation, and this will give you the those values, and then try to analyze them, and you keep doing till you get consistency between your previous gamma and the current gamma and previous beta and current gamma plus and so minus value to be to each other. At that point, we should keep on doing this. This is the consistent way of. However, when we do, what we have seen is again you see like a mean, but this is so we have something, but whereas gamma is going to mean like this is for some the most important issue in the literature is that the data which is analyzed using the image isotherm, data which is analyzed in literature is typically taken on the data which is outside the asymptotic. The single power law should be used in the universal impact, and that is and I think due to lack of whatever we are trying to this you are supposed to have the 3D Heisenberg value, but here it is still coming mean field like value, and that is still changing in this second decimal. That is so-called asymptotic critical region is extremely narrow, even if you are by so this is the entire point which I was the interactions are intermediate kind of interactions. Generally, 3D interactions are supposed to from RG calculations we get the value of sigma which is greater than 1.5, which is just that not so the next nearest neighbor is also possible. That's why you have and they are doing the same stuff. Between the and further, there is another way where people are just trying to look at state. They are also trying to get this. But, they try to get oh, as this what is it? And back to that, just to put the macrotonic effect here only to tell you that macrotonic effect to ascertain or simply assert that this is a second order phase transition. Macrotonic effect will not be able to tell you what universal is. Though people routinely use it for description, but then you see whether mean field exponents or the exponents equally describe the macrotonic data. Macrotonic effective macrotonic data is so to decide the universal. So I'm just trying to tell you the same point. The point which I'm just trying to tell you is this particular system, picture of magnetic order disorder transition is typically governed by isotropic short-range Heisenberg interactions, unlike the various reports that are there in literature, which is pretty the analysis is used as the single formula with the interaction.
Yeah. So it's very good talk. And just one is small question. Yeah, yeah. Graph which you made. Yeah, yeah.
Which graph you want to say?
All graphs which you have made, you have designed these graphs or you have taken any graphs?
No, we have done. We have done. We have. Yeah, that is experiment. That is. Yeah, yeah, yeah. It has been analyzed and then been plotted using origin. No, no, no. We have just used the origin software. Yeah, we have taken from literature and that analysis we have done using Fortran program. Yeah, yeah.
Yeah.
Okay, thank you. Due to time constraint, we cannot take more questions. In the online, no, later. Online stuff. Would you say- So next talk is by Yogendra Kumar Mishra, and he's one of the renowned scientist. He's very good, renowned scientist, not only in India, abroad. Yeah, Yogendra, can you hear me? Yogendra.
Recording in progress.
Yeah, Yogendra, can you hear me?
Yes, I can hear you.
Yeah, welcome. And I suppose that you will come personally and give a talk.
I'm very sorry because this day was already planned here in Warangal, so I'm here in Warangal. And
Yogendra is a very renowned scientist. He's the fellow of Royal Society of Chemistry. Okay, so Myanmar STU. Before this group on 3D nanomaterial at functional nanomaterial scale, university detailed where FCU SYD smart material group's main focus is to develop a new class of functional material advanced and system. Board of associated for many prestigious journals, magazines. He has received many notable awards like collecting the World Humboldt Fellowship and the Young Investors Award from BHJ London, Denmark, and he has won several successful published more than 50 books, over 20,000 citations and index of 76. Okay, so it's over to you.
thank you very much, Mukesh. The most important is for your kind introduction, and most importantly, where are the raised in this again in very next my if I'm trying to share sales books and not allowed, it's not allowed
You have to accept. You have to accept.
to allow
Yeah,
that.
I think they allowed you.
Still not.
Just a bit. हाँ कर दिया देखो.
Yes, now I
Yeah. It is time lag from north to south.
perfectly fine. One second. Want to say. So, what do you? Do you see my
Yeah.
screen?
Yeah. Can you just move? Yes. Perfect.
Thank you very much for the invitation, Professor Sharma, and I'm really missing you. Yes, I want about the smart materials we are working with, the kind of research we are working with to put into smart. this beautiful image is there in the bottom of the box, and we can be my what you have to put. Very nice. It is. They are very much aligned. Where is it? Know where do I come from? So then there is a mark some things you are wondering about where where you have been about on where university and make a university. That's how the name comes from. Universities they were very nicely. So we have quite many PhD programs and over 1,000 employees. So well, the key name is Thunderball, and there is also the Navy company named Danfoss. This is a very big one of the company was in the what what about the drive left on the road and remote people and over because we have a university campus so that is working on that from so what is this university West Lawson was the kind of well that's from the introduction. They also sponsored the example of academia industry collaboration. Our problems are research problems are straightforward decided. We have developed world-class infrastructure, including development, very dynamic integration of national speed. The chance like it might be come over there. Let's work the big problem. The three dimensional communication today nanoscale we know very well the kind of dimension of the material nano very material is the defect and the and nanoscale maximum that's the whole material. Well, the intermediate conclusion is last five hours growth of nanomaterials any can understand those properties, the properties next week we have now uh, Thanos consulted the mind as that these Well, probably more than several billion. Nanoscale material. Can we go to the market and sell a product reduced from what is products is created? When we have business development into the society, then the materials on mobile phones, we need to use, we need to kind of really for one but we are not able to translate nanomaterial into application. Very simple, very and that is a challenge. Well, where to the even if you want, for example, if you want to make a device, why out of nanowire, we need a nanowire, we bring nanowire will integrate it using the control. Well, it's not my with kind of making device, conventional approach and some development very good way. My idea was it nanomaterial. Then I could read nanoscale surface in efficient way and the kind of into the and this is the perfect example of that we feel out in the same way. Materials, how to get basically such a material. We could go and talk back in the same way like we talked 20 years ago, top and the bottom of the approach. What approach for the multi you know, really going to develop it. Well, a very simple process that reports of zinc oxide. So before starting the research with zinc oxide, one should know a little bit. If you want to research the literature, more or less imagine is published already. Usually, the novel would have one can nearly know the morphology out of zinc oxide. Why is it so very robust material due to the orthogonal structure? One, this is really a kind of but then kind of not work with zinc oxide and otherwise and working and kind of things in the approach is material point in Mumbai. Public transport, the cross line before the water. There is the reason behind it. Doesn't matter how you put them together, they are able to form a kind of in a way random or some of my nano world the three-dimensional. So I have kind of grow micro and nano scale that report from data marketing from morals and small last 5 years it is kind of very few may be wondering how the process was the oven is covered material person from the kind of will throw it out, but in nanoscientists will never throw out because it could be of carbon. Let us check it. The same philosophy could be extended to the recipe in our by the part but pipeline. The talking about now towards the plane is lifting up these kind of microparticles due to the plane temperature, these particles are converted to atomic vapor, oxygen solid growth process. When we grow, basically one is structure, one can mount the will was of nuclei like this is the C axis of what material. These micro and nano are grown. Typically, the process looks like this. This is the process going on. How the crucible looks like, and then over at 900 degrees for 30 minutes, the crucible is filled with how they form in the degree of porosity. Basically, the step mainly controlled by the oxygen content. So we may kind of apply here along the C-axis, and in this way, if we supply more oxygen from the micro of support. This is inclusive. From then what happens? The larger is smooth, the surface is having lot of their base structure, and this is really adding a very unique. Know the advantage of this tool from our daily life and surface so very nice. Proper so very simple assembled network. The similar and imagine if you glue each software network, similar analogy was applied. All afterwards, heat 1150 degrees centigrade allows the formation of dimensional interconnection networks. We were not limited to any size and state. These all these networks are having a density of 4.3 grams, velocity of around 94. inside these networks, like, are really multi give you some in the next 20 minutes. Basically, I had in the beginning, I that reports network quality as work quite well. First of all, I the very much right so much finance this is a wide band gap material with something is something that start with the same I was starting and something with you device decrease a bit of the biological sensing biomedical mind the biosense to diagnose something earlier maybe better detection. And that's where the nanomaterial well visible sometimes the things are of devices sometimes the high temperature into the high temperature environment and once it doesn't you best bio finish ready to be how challenging that kind of level because I know what amazing I take places here to send it else and sciences really the selective content being a science is a very kind of robust can put it all anything happening where those challenges are developing that support for this and human meditation to come really towards it like this. Well, very recently we demonstrated even the nanograph and the oxide now. Geometry really hard to understand kind of really made us the people like critically demonstrated how the other arms are bending like this. And then the overall piezoelectric is accumulated in the what we demonstrated that output voltage in like like full total that just crystalline gets it feels the electrical conductivity. But very recently we also demonstrated as a kind of we know now what is as the going on in that why somewhere we have to really work on the course of the fine tuning our airplane thing more kind of only just right and when we feel we are always about the kind of agreement required, and that novel because it's a method composite engineering really helps us much even we can join only using the pillar material as a if I want to distribute nanoscale particles, molecular elements, like matrix, do it in like chemistry, fluoromet, nano, use the pieces was the feature that they found out we are voting in somebody doing and members of the parliament, there's an internal damage. Have material composite damage. Waiting. Okay, material is changing its there are requirements for demands and set report. And this was really this could be used as a nice and how. So I mean the composite engineering and weeks and months we have been and post coatings and stuff. You know, really crazy. The new material we are way up. I wow and then we multiply multiply our nanomaterials viruses are negatively charged. Viruses in the virus envelope is negatively charged. Definitely. And one be eliminated with global identity. Well, start paper, then more motivated in virus, the third virus, and against 10 different viruses, and the performance has been really, really nice. And important cycle, the three-dimensional state, the materials flow around us, yes, and then we basically end up how the animal, and this is genital herpes virus, just do kind of figure the cells when some gene science the much faster. So this is the results positive Basically, there's a little product in the market I will tell about a five-stone company in steel. It's something the lesson we learned during the my trip. The doctors have been giving zinc these tablets to survive. And basically, what I'm doing is because the little metabolic things zinc oxide goes into our body. Yes, it is very important. Believe me, before starting kind of research with viruses, I had in brain that yes, one kind of virus. Now I comment always that after Corona, virology is working on it. I'm very happy to announce that it is available in Amazon. Very, very vitamin C increasing the work by from here. This year they have well, because just one case I can one is only very, very small. As I would like to begin using nanoparticles to catalyst. They were basically diving innovation and very nice people. But we are not reporting very often things that my nanomaterial into the water. And problem today, microplastics in our. So the question is there any way? Yes, 20% possibility to monitor finding the material. Since these reports are long, they are not very use that kind of thing, but at the same time, we have the possibility to monitor that. In this way, we still consider there to be one thing or like nanorods on the top and then encapsulated in the water. And basically, the beauty of the material is that if we have met our functional requirements, for example, on the other side, we have the metallized. We really design iPhone monitor kind of the health of the material for particles, etc. Much more in the direction of chemistry application. Well, we have the lack of time, so basically months and kind of years. But we have well, no, not the one who decide how materials should grow, but here we develop a new process can kind of develop the new material and remove the backbone. For example, solution renum of hydrogen. Now this is the composite material. This is the composite. If we want, we can remove the underlying bone. This material in much more porous that we can variant carbon polymer basically graphene. engineering, where we are and for example, this is three-dimensional plasmonic nanoparticles, for example, and so basically, first I knew we spoke the direction of materials engineering, whatever functional equipment is willing to begin hands on the well, last minute I was kind of even with good like support volleyball community treatment was used as a favorite membrane behind the and both. And then we got motivated. Let's put yourself. We just made it. We just our demand that will basically these are advancing. Well, I don't know how much time I have left already, but I am at the end of my last slide of the talk. Rather than out, I was told 15, 16 years ago not to work with tetrapod, and then I checked find many more of us. They didn't create material of life. Yeah, already have some of the person is chemist, a biologist, a doctor, and or even kind of a robot guy, composite guy, everybody has different and different definition of zinc oxide, but one it is the same material. It's like now the different. I have been trying to put this together this in a very nice way and be very successful. Not one smart in our about. So when last I died. So because of them and till today what I am and thanks to good foundation, good development, money was doing one fellowship 9 and 2000. Basically, and then funding family they need to promote it. So I'm really happy that Martha have really worked very kind of this have been this going to work in the very much for getting the talk and everyone for getting the talk and I'm looking forward for any comments. Thank you very much.
Yeah, it's an excellent talk. So, it is open for question. पूछ लो अभी मौका है मिलेगा नहीं
नहीं, मौका तो हमेशा रहेगा। Sir would like to conclude. Okay. What would you like to conclude? Yeah, it's a very nice inspiration. Usually, what if you put the architecture random area for a city, so you make put a random is diverted right from the base. For the thing you are depending put article at the end or when you get the point like yeah, and this is because of the which is coming for like on my for an inspiration I told you. Did not
Oh, no, installed.
hold it. You want to convert it? No, they installed it. This was developed.
That is a size shape don't need some kind of physical magic. Whatever manner you will working adhesive.
So I am talking about basically this is the basically I am more narrow sample version. That is
Any other question? What related to health you are talking about? Okay, so I have one question.
yes.
So tetrapods are now kind of sensing the body. I read somewhere they can sense the nerve. You
I
can just
I would not comment on the next sentence. This is put into the medium where the nerves are there. That I can confirm, but not really sensing with nerve. This has not been done by nothing about
yes.
yeah.
And it can be sense and can sense nerve. So home can sense the breath.
Yeah,
So this will be a good collaboration for both of us.
I have to visit New
Yeah.
Delhi and
Yeah.
into the
So I
yeah.
and
Please
only
find
only
the
and only I have in India.
please find the biomedical park.
Yeah, yeah. Thank you. Thank you. So since you are online, we cannot finish through physically, but
I have no question. Thank you for the
Yours, Professor.
So my question is like the human body organelles, they are in the order of nanometer as well. So,
Yeah,
I'm discussing inside the cell. Inside the anything. So
yes.
uh, like how can we get to different domains of science in nanomaterial? There is the biomaterials that we already we have inside our body.
100 pounds. We have all dimensions. We talked about nanomaterials. Nanomaterials are to destroy something or to find something as a carrier, more or less.
Okay. Further, I want to add some more points. I was just asking that human body is animal cell. It's an outer of microbiome. So if you go for the organ, mitochondria, whatever I the bio I know, I think mitochondria and RNA, DNA, and all those. The life and the molecule, order of, so they had the order of the kind of it. My question is like how we can connect bio with the body. Maybe is it what is the real world today is a working experiment.
Yeah, but the
Different domains.
be honest, what are the problems in your the non-address either sense them, just recognize them and tool. So now they, that they can easily penetrate inside the what no person but how effect we want to achieve the health. I don't know if this is an answer you are expecting, but this is something I would like to comment on. But there is a very big interface. The only similarity is the length scales are really matching. We are nearly in the same length.
So, if anybody have more question, now question. Ravindra actually, thank you very much. Excellent. It is due to Delhi.
Thank you very much, and I'm looking yeah. Have a nice day. Bye bye.
Shivani, so Shivani, we will cut your talk to 8 minutes. Okay, and he's already gone. किसी पूछना है ना? नहीं नहीं. Additional talk. हाँ, your talk is there. Your name is Rajiv Dwivedi and Mukesh Verma. Have two more talk. That's why cut it minutes and do it fast. So it's better. Yeah, Shivanani Gangwal is from Doon University, and she will talk about exploring the and machine administration, evolution, and device. I think enlightenment का कोई दिक्कत नहीं है. केस फिर उसकी दी हुई है द्विवेदी। हाँ शिवानी शुरू करो।
Good afternoon, everyone. Myself Shivani Damwal. I'm a research scholar working under the supervision of Dr. Himani Sharma. The topic of my presentation is exploring the interfacial properties of 2D-based TLDC for efficient hydrogen evolution and device fabrication. So this is my presentation outline. In order to overcome this energy crisis, a clean source of substitute is required. Hydrogen has emerged out to be an effective substitute because it is renewable, it has high energy density, and almost zero carbon emission. Using hydrogen, one amongst them is the electrolysis. In order to using electrolysis requires an effective catalyst. WS2 has a good electrocatalytic stability, low cost fabrication, electrical conductivity. In order to improve structure, one has had an internal field develops from the pointing from the direction of reductive to the oxidative side. The presence of external light source band in both these semiconductors, and since an internal of the semiconductor and holes in the oxidative semiconductor can be utilized. So the heterostructure which I've chosen is WH2TAO2, and negative conduction. That's the heterostructure catalyst to hydrothermal synthesis was utilized. The samples were characterized XRD and number. Indicated the fields corresponding to 002, 004, etc., which confirm in case of TiO2, fields saying which were also present in the heterostructure. But in case of the heterostructure, they were shifted slightly towards lower wave number, which likely due to the presence of tensile. Furthermore, the samples were also analyzed using Brunner Emmett-Teller in order to find the surface and increase we also determined the morphology structure as also present in the cross-sectional image. Different layers were shown. For HR10 images, confirmed the lattice springs corresponding to in TiO corresponds to 110 which is also in collaboration. So the lattice springs WS2 again. For interfacial investigation, first external analysis was performed, which confirms the presence of W, S, Ti, and O. Of the heterostructure, there was shift in P position towards lower binding energy, which proves the presence of charge transfer on forming the structure. Also analyzed the band gap sample. As a very electron spectroscopy was performed in work function, a lower value work function the onset values mass and position, which were then in order to get the final energy band diagram. Samples were then characterized and tested for the hydrogen fusion reaction studies, where the first figure shows the linear spin photochemistry test, shows a low value of onset potential and high current density, and also a low value of taper slope. But there are more electrochemical. So, again, maximum was obtained for the microstructure. The microstructure has a better HER or catalytic performance as the best. We also fabricated a device based on that. This we used because there's can be can also used in harsh conditions. This is the
1 2 question. One.
so tunable band gap means the band gap of the WH2 or TMDC can be modified either by doping or by forming the heterostructure. For example, in my case, WH2 had crystal sample around 1.6 electron volt. But when we form the heterostructure with on combining with that, change. Similarly, by doping or any other method, the altered gap values
Okay. Thank you. Thank you. Thank you. Now next is Rajiv. Rajiv Trivedi. हिमानी नहीं आई क्या? है? हिमानी को बोलना सर थे वहां पे. You know my name? ठीक है मुकेश जेवलिया.
मोटिवेट कर रहा है या मोटिवेट कर रहा है पहले?
मोटिवेट कर रहा हूँ. So Rajiv is from Bennett University. Rajiv.
Good evening. Good evening. Good evening, everyone. Good evening, everyone. Myself, Rajiv Reddy. I am PhD student in Bennett University under the supervision of Dr. Sachin Gupta and collaborated with Dr. Dinesh Konsupla, UGC DSL Indore. Our topic is the investigation of the scientific nature on the plan of my presentation, introductions, and motivations. Yeah, multi-ferrite material is having two more ferroic properties simultaneously, such as the ferroelectricity is ferroelectric is the instantaneous ferromagnetic is the spontaneous magnet and ferroelastic is spontaneous अपना multi-parent this combination of magnetic and these figures also how can identify the make a multivariate material in using this from kind of material. Yeah, applications of the multivariate material application coupling between magnetic and electric field and produce the electric field and find the magnetization of the electro electro coupling. So, what in this there are found the using this is the DC magnet and this is the hand applying the AC current and produce when apply the magnetic field, they send sample with the piezo-magnetic and create an are sensitive and the thickness of the sample. Composite and why in this reason is the major subject I chose in the magnetic nature of magnetic material and so and so electric material and would multi-fluid nature. And medium tension is the best not for the electric material. These are the and dielectric material. So these are the person behind this using the both material are the stimulation for the study of the material. They are in additionally we are in that region our substituting dope utilizing cobalt when dope so our magnetic flexibility have also increases and anti-radiation are cobalt from iron or titanium. Here we are we we take and make a composite in 70% ferric oxide. And here composite are same composite are sentenced to centered. These composites are for study the exciting these are the exciting data of the my company. Composite is the pure beauty and these here that shows the multi-fluoride composite nature. Here in exciting graph, both nature are showing in our composite. Here, efficient data is the increasing Grain size are also after grain size improve the in grain size are also learned its various properties of improve showing. Showing the dielectric spectroscopy data in room temperature increasing the frequency dielectric constant value of uh, also increases the but the dielectric also here showing the temperature dependent dielectric and different uh, so on here showing the increasing expected to around room temperature. Room temperature that is the clear relaxation behavior of this also here we verify the our composite. This is the fluid and magnetic also between pure titanium to ferric oxide. Ferroelectric. This study for the ferroelectric nature are showing the compared to barium titanate and mixed composites. And these combinations magneto and we produce a voltage in again previous slide and increasing the shrinking temperature and more than 50 or 50%. This and the our properties are also to visual these are of the light is increasing the shrinking temperature. The various value of visual electricity and increasing kinetic also in the good relaxation behavior also.
Yeah, one quick question, only one. If no, then thanks to speaker. Thank you very much. So next is Mukesh from St. Louis of Rajasthan. Mukesh, Mukesh की PPT कीजिएगा on. This is the last talk. After this, there will be a panel discussion. नहीं है? Directly. Okay, good. You have just 8 minutes.
Okay. Good evening to all of you. I am going to present magnetic and transport properties of equality of dimension LE 1.4 SR 1.6 Mn2 O7 magnet. Followed by introduction about this magnet, then motivation, structural characteristic morphology and chemical include this. So basically, this mainline is gross production capacity, LA and minus LA, MNL O plus 1. So here N equals to 1, then this will form this type of center where this also equal. And when we use N equals to 2, then these two amino acids of tetra are equal. One here, and I bracket my line. When we like a pyramid like this, metal insulator metal kind of layer. For practical applications, we artificially make this tunneling magnet resistance junction where we use two ferromagnetic layers separated by insulator layer. But this material is naturally around 1%. But the mechanism behind MRI clear. So there are various sensors and magnetic devices. And in future, we are trying to use the properties of devices. This system, it was observed that it shows some skull marks. And we figured that answer for this particular composition set. Here, this is the room temperature SRT data of the system. This was prepared by solar. So, all floor calculating the flat size. Nature of this. So 5% is negligible and good. This sector is as we are expecting that two years local is currently this MNO2 plan. So the magnetic barrier and other but every has local layer. This sector and we go. This is my morphology and chemical analysis of this sample. Here we see the sample activity nearly uniform regular began with an average grain size of approximately 160 micrometer. If this size is greater than that flat size, the one grain is this area is full. This is the magnetic data. This measured at this is paramagnetic, but there are many inflection points. Then these three are important. One is the transition from 3D ferromagnet to the 2D ferromagnet to paramagnetic transition. But this inflection point two that is clear that is the primary source of inflection. Then this blue data is temperature dependent resistivity measured at zero magnetic insulator to metal transition. Generally, this dip is observed for this inhomogeneity of sample, but here this is not this magnetic property. Measure magnetization data is different. Here we can the bifurcation then we are increasing magnetic field, source of energy. And this for pregnancy. Here, generally it should increase or shift to high temperature when we that at low field there are some anti-magnetic vibrations are present. And here also when we are increasing there that is happening that conditions also present. This is the irreversibility uh, full magnetization and the zero field. And this theory is a strong irreversibility where this is floated at a function of one fluorescent. Here, this is and then opposite of this T bifurcation. Here also, flow field it is increasing than decreasing. So here you can definitely say that as low field, there is some just showing paramagnetic kind of behavior. For high magnetic, low temperature data, magnetization by using this uh, where this there is the here T button dominate where our system is so infinite nature and the T is able to when we our system follow the localized nature, but we at the high velocity that is much higher frequency. This is the magnetic region and each from like by using this modified Curie with law and that gives the level of magnet. Generally, it is shown that for breaking field, magnetic is so this is magnetocaloric effect in broad temperature range that may be useful for with that Johnson is that goes uh, this is the magnetization. We obtained this is that one repeating also. How they are coordinating to each other system. And collaborators one both samples and the central instrument facility for providing CSIR for SRF and follow.
So any question? You are measuring the oxygen. क्या था मतलब इसमें जो है ना ऑक्सीजन कंटेंट मुझे वो it's hard to quantify from EDS. I mean,
Yes, sir. That's why I am not here talking about the composition. I am just saying that these all elements are
except oxygen.
Normally we do double completion.
We are now at the end of the session, and now floor is yours.
Now it is time to carry the field. He has done a lot of hard work. He has been carrying the session. Senior from Root. Then myself. He is my So now it's time for high tea. We prepare for the culture program and outside arrangement has been made for high tea. So please join us.